Hello, my name is Roger Torvald, and I'm a faculty member in agricultural and biological engineering at Purdue University.
And I'm Richard Fox, and I'm IT person here at Purdue.
Today we're going to spend just a little bit of time talking about robotics from the standpoint of this particular project you're all working on, how you might integrate robotics into the system. And then we're also going to talk about the fact that robotics are becoming a very common feature in agriculture. We've got a lot to do yet, but you're starting to see more and more robotics. And when we think of robots, we might think of the walking robot. We have automated tractors that are being tested. We have automated feeding systems been around for years. So robotics have been around in different forms and shapes for many, many years. So let's look a little bit at some of the learning objectives for this project. One is we want to be able to have the students understand what the advantages and disadvantages of robotics in agriculture. Some of the advantages you might think about would be, one might be labor. If the system's automated and does it by itself, you don't need as much labor. Some people might say it's a disadvantage, so taking jobs away from people. But what we hope will happen in the future is that by taking out some of the, say, mundane tasks that are boring or repetitive, and taking those out and taking that away from people, then individuals will have time to focus on maybe more technological issues that we need to look at in agriculture.
There's also some safety concerns that this automated system could take the human out of that situation.
So, for example, when we talk about automated tractors, who's going to determine if that tractor stops if somebody walks in front of it? That could be a safety factor. So there's a lot of things that are still kind of up in the air that we're still working through on the robotic side. Another one is we want the students to be able to understand what are the basic components of a robotic system. And we'll talk about those in a few minutes, but there are three basic components of every robotic system. And then we also want them to be able to understand and explain the importance and function of those basic components. Why are they needed? How do they interact in a robotic system? So let's look a little bit at a robotic system, what they're composed of.
It is an input system.
So our input system might be like a camera. And we use cameras everywhere. You think about the Tesla automated cars or any of the cars that you see that have some type of driver assist or a automated driving system, they have cameras everywhere. So that's one common type of input device.
A controller.
An example of a controller might be, it could be a computer, it could be a full-blown computer, or it might be a microcontroller board like a Raspberry Pi system.
And we have the output system.
And again, a prime example of that would be a motor. And there's others we'll talk about as we move through that. So those are the three basic components of a robotic system. So let's look a little bit at input devices. And an input device is a system that receives information. So when you have an automated system, you have to have something that collects information, data, and feeds that into your system. So some examples, and this is not a complete list, but this is some of the examples that you might see. One would be optical, and again, that's like cameras. Physical, and when I say physical, it's like maybe a bumper switch or a pressure switch that would put pressure on something. Maybe the robot runs up against something and there's a switch that's activated, and then that gives feedback to the system. Audio, microphones, and we're going to see more and more of that. We see that some today already, but getting audio feedback into a system.
And we have thermal, which is thermocouple, which basically reads the temperature of either the soil or the outside temperature, and these are found all over the place.
Proximity sensors. And we see these today in some of the cars that we have. If you have a car that has the assist that slows down as it comes up behind a vehicle, you have your cruise control or speed control on, that's a proximity type sensor that uses different technologies. An example might be like laser, or it might be ultrasound, would be a couple of examples of that. The second part of the system is the controller. and we might think of this as the brains of the system. But it's the part of the system that usually has some coding involved, because we have to have some coding behind the system, because robots at the very basic level are dumb systems. It's what we program into them that allows them to perform the different functions. So you have to have the brain or the controller or the system to do that. So a typical controller is a microprocessor. Some examples might include
Raspberry Pi, very, very popular out there, and a lot of different code for it.
an Arduino, which is again another microprocessor controller, again very popular.
And basically your PC. Sometimes you can just use your personal computer and run the code on it and have a USB connection to it, and it'll do everything you want.
Output system. So we've talked about inputs. We talked about taking that data into your controller or your brain, and then that controller or brain makes a decision based on the coding and feeds it to an output system that then performs some action based on whatever you want to accomplish with your robot. Some examples might be, and one of the most common is a motor.
Then you got the servo.
And a servo is a kind of a form of a motor. A motor has continuous motion. When you let off power to a motor, it stops wherever it is. A servo is one where when you let off power to it or voltage to it, it goes back to its normal state.
Then you have the linear actuator, where it basically takes that output and creates some type of linear action, some type of movement, and generally it's done by a motor through gears, but it is a type of linear action.
And then your pump. It would be another one when you need to move some type of liquid, for water as an example. So pumps are also very commonly used as an output type device. So let's just take an example of a robot that's been built here at Purdue students, and let's just look at the three key pieces of the robotic system. And this particular robot is a robot that's designed to go through a cornfield, identify some different weeds, specific weeds in a cornfield. Then once it identifies those weeds, it's supposed to eliminate those weeds. So looking at input devices, since we're really looking at weeds and we want to identify specific weeds, we have to have some way of taking a picture or an image of those weeds. So under the canvas on the front of our system, we have 6 cameras that are constantly taking images, video images, feedback, then it feeds it into our controller system.
There's basically on the cameras feed into, and it's hard to see it, but it's basically just a general computer right here that is taking those images in, and it's processing, it's looking, and it's comparing on to a database to figure out if those weeds match.
It's basically a matching game. So it has a big database of pictures, and in simplistic terms, it's taking the image it sees, and it's taking it into the database and saying, oh, it's a match, that's a cockabur, for example.
There's some interpretation to it, but it is in simplistic doing a matching game.
So once the computer then identifies camera 1, for instance, and we have the cameras numbered, if it says camera 1 saw a cockabur, and we know that camera 1 is located right here inside, then we know that we have to deploy some type of system to get rid of that cockabur. And we know that camera 1 is looking between the rows of corn. Camera 2 is looking on top of the row of corn. So the camera that identifies the weed indicates the location of the weed as far as is in the outside row, is in the row, between the rows, etc. And then it feeds it back to our output device,
which is basically a rototiller, these 3 orange things, and has linear actuators, and it basically just races that up and down. And then we have, within the row, we have some solenoids, which basically are on off. That's another output device. And we basically turn on and off this flow of liquid to spray on top of the crop, depending on what the weed is.
So this is a fairly complex system, but you can see just like any robotic system, we have input devices, we have some type of controller system, brain if you will, and then we have our output system that takes action based on what is input it into it, and based on what the controller says. So now let's look a little bit at the design challenge for this particular program. Your challenge is you're working on microgreens, growing those, and then we're going to look at how we process those. Your challenge is how can your students, how can we determine what is the most efficient moisture content level for the soil and for the air, humidity. So your challenge is to design a system that will keep the soil moisture and the humidity in some ideal range, and you have to identify what that range is, and then to design a system that will keep the moisture in those ranges. So, all engineers, when you talk about engineering design, there's various models that talk about the engineering design process. I have a very simplistic one I like to use because it's easier to remember. The first thing you have to do when you start looking at solving a problem engineering-wise is you get into the design phase. And that's a lot of research. You're going out and first you got to ask questions of what do I want to measure, what do I want to solve, what problem do I have. We already said the problem here is identifying the moisture level content of the soil and the air, humidity, and then keeping that moisture content within that acceptable range. That's the challenge. Another challenge is how do you design an automated system that does that?
And this is kind of more of the fun one, I think, because there's no limit other than what you're supposed to do. You got to find anything, have any type of design plan that you want. It's just kind of all open.
So the important thing here is try not to limit the creativity of your students. So don't, for instance, say, well, we need to go get this device. It's better to say, here's the problem. We need to measure, for instance, soil moisture. Let them figure out what different ways that might be done. For instance, we had the ag bot and we had to talk about getting rid of the weeds. We never said we're going to do it mechanically to our students. And so we actually had the students come back and say, okay, let's use lasers. Let's burn them off with lasers, which we actually did research on. We actually had some say, well, why don't we just take a bunch of flamethrowers and burn them off? Then we looked at chemical and mechanical. So try not to limit their creativity. Leave the questions really open so they can go out and find different ways to do this, then as a group make a decision on which way they want to proceed. The second step is once you really went through this process, and then a lot of time, a lot of research, and it takes a lot of time, and you spend a lot of time, then it's the fun time. You get to build it. So based on what the group decided, then you start buying the pieces, and you start building them. So it becomes and you may have to jump back when you see the arrow both ways. You may at times jump back and say, well, we need to do a redesign. It didn't work out the way we thought.
Cost, it could be too expensive to do it that way. There's different things, but the build it brings it to reality of what you thought.
Then once you've built it, then you test it. And this takes a lot of time. But the important thing here is you have to really think about what data do you want to collect as you're testing it. And then you move into improving it. Okay, you build it, you tested it, you've gotten input, then you evaluate it, see how you can improve it. And then, based on all that, you may start back through the process again because it maybe didn't work the way you wanted it to. So then you have to say, well, redesign it. How do we fix it? How do we change it? So let's look a little bit at this by-step process. So again, on input, again, I mentioned before, raise questions of what do you really want to determine? What do you want to measure? What do you want to get done? So it's a really broad, open-ended question. And again, what I would do, I would assign students in groups. It could be groups based on size, or you may have one larger group, or you may subdivide them and have them go out and they start doing research, looking for different types of ways to identify the soil moisture content level and the humidity level. And after a lot of research, they come back, report to the groups, and may do more research. Then eventually you come up with a agreed upon plan by the entire group.
And then you need to decide what controller you're going to use. There's a lot of them out there. We mentioned two, Raspberry Pi and Arduino. But it's basically going to be the brains. It's going to be what you're going to put, your input, your output, and what code you're going to put on there to basically come in and interpret that input and do that output. Some of the things that may play into this is what your students are used to maybe a little bit, or what experience in coding they may have. I mean, there's different things like that. Most of these have a lot of example code out there. These two especially. It's real simple to go out and find some code and some examples, kind of get you started and figured out what you want to do with that.
So as Richard said, probably one of the more important things here, maybe in your case, would be what are the students familiar with? Because in this case, the Raspberry Pi or Arduino, both would be acceptable and good solutions, but if students are familiar with one or the other, it may be a deciding factor. So output, again, how are you going to correct the problem? We already identified what the problem is. You've got some data now. You've got a control system that's going to take that data, make decisions. Then how do you apply your action? In this case, if we're talking about soil moisture content and humidity, how do you increase or decrease the moisture content in the air or in the soil? So you have to think about ways that might be done. Maybe a pump, maybe some type of spray nozzle, maybe there's other ways to do it. So again, the student needs to do some research and see what are the possibilities out there.
They need to also make sure that while inputs generally go straight into a controller, outputs generally have some type of control mechanism, some type of interface between your Raspberry Pi or Arduino in it. There's a little extra step on an output usually.
So build it. Again, we kind of mentioned this before, but caution, and I'm going to say this over and over again, students really like to move to the build it stage. And I don't care if they're high school students, college students, adults, we all want to get our hands on something and start building. It's really important to not undercut the amount of time you spend on the design stage. The design stage is the most important piece. If you don't have a good design, then your build is going to be poor. It's just not going to work as well as it could. So, I can't re-emphasize, make sure you spend enough time on the design at stage before you ever move to the build it stage.
Because if you don't, you're going to go right back to design, you're going to waste that money and have to go back and redo it again. If you got a good design, you can start tweaking it and continue to hone it in.
Then test it stage. This is data, data, data. So the important thing I want to emphasize here is before you really get out and start testing your system, you have to really identify what data do you need to collect. Is it the amount of water that is running through your system? So you look at efficiency. Do you want to measure that? Do you want to measure the amount of time the system runs? There's a lot of different factors. So analyze it and identify those questions that you want answers to so that you can collect the data when you're doing your testing.
And actually collect that data. Put it into a spreadsheet, whatever, on paper. That way you can go back and reference those numbers. Don't just adjust, oh, this was a little high, this was a little low. But look over the whole data set.
Then evaluate it. Again, that's where you use that data that you just collected to make some decisions about how well your system worked or didn't work. And so again, as Richard indicated, it's really important that you put that data into a system so you can thoroughly analyze that data so you can make some decisions where your weaknesses are in your system. And maybe your system works. And when you evaluate it, it's not that you may say, well, it worked. The question might be, how can we make it better? And engineers are constantly looking at ways to improve systems. Systems that work, but can they make it even better? And so again, it's really important to make sure you understand what you are looking for from the data standpoint, so when you evaluate it, you have that data to make those decisions. So, you've been through one round now. You've designed it, you've built it, you've tested it, and you evaluated it. And you found things that worked well, and you found things that didn't work well. So now it's time for round two. Because engineers will go through this process over and over and over again to get the best system possible. At some point you have to pull the plug and say we're done, but you're constantly looking at how you can make it better. So, again, in round two, you're going to use the data you got in round one, and you're going to do maybe some redesign, some tweaking, not a major redesign hopefully, some tweaking of the system, some more testing, designing, etc. So again, as I said, engineers are constantly redesigning, rebuilding, retesting, and reevaluating. So one thing that, for your students, remember it can be very discouraging to the students when they spend all this time and it doesn't work the way they thought it would. We all get discouraged when we spend time on something and we think it didn't work. The important thing from an engineering standpoint is not to think of that as a failure. You've learned a lot from that process. Now take that information and make the system better. So it's really important that you celebrate wins. And they may be minor little wins, but you really want to keep your students pumped and excited. So when things go well, you need to have a celebration, pat them on the back, whatever the case may be. Say, man, fantastic job. And so there's going to be a lot of times when things don't go well and you can get very frustrated and depressed. So again, it's really, really important to celebrate the wins.
That's true. It's undoubtedly, because they are going to be failures, no question.
So I hope you have a great time with your design process as you look at how you measure the moisture content of the soil and the air and how you control that through some type of automated system. And as always, if you have questions, Richard and I will be available through this project to help with your questions as you work with your students to design the best system possible.